The last one, so 10 is pretty, 11, 12, so that's pretty good. For most students, this is memorizing is about 2 years easier than how hard is the final? It depends on how you study. So because I will tell you the types of topics, and there's 40 questions that are all previous questions. Okay, 40 topics. So it's hard to remember everything we've done, but hopefully, like if you know what's in the third, like you know what's in the yes. It's 20% of my which can help you if you do well, but if you don't study, okay. All right, so I'm just gonna pull up lab 5 really quick. This one is. We're not going to go too much through the pre-lab because I think you guys can figure out the pre-lab. It's just mostly in the questions, in the instructions. But let's go through this. So if you pull open the instructions, you can have these open while you're doing the pre-lab. You can use it's like open world while you're doing the pre-lab. Okay, and you kind of go through. The first part is you're going to get a set of chemicals. So the idea is what happens if you come to your lab, you had 6 things together and somebody knocked them all over and they're all out of order and you have to figure out what is in the bottle. Okay, so this should never happen because you should really very carefully label all of your vials, but this is like, if this happened, how would you figure out what's in the vials? So this is what you're going to get. You're going to get a spot plate. And so we use that because we can use small amounts of the materials and we can see if there's a reaction. We can quickly see if there's anything that's happening. And it's also on a grid system, so you can figure out really easily what's going on. Okay. And then you're going to get these 6 solutions. So some of them, you're going to have one set that's labeled and one set that's not labeled. The unknowns you have to figure out. You have to figure out based on these 6 things that you have, which ones are the unknowns. Does that kind of make sense? Okay, I'm not explaining this super well. So that's part 1. You can also use things like color. Like some of these are going to have a color. If the known is yellow and nothing else is yellow, then probably the unknown is going to match the color of the known. Okay, and then what this lab wants you to do is to mix them. So if I have 6 knowns, how am I going to figure out what the unknowns are? So imagine you're going to mix 2 of each together. So I'm going to take copper and mix it with iron. I'm going to take copper and mix it with nickel. I'm going to take copper and mix it with sodium hydroxide. I'm going to take copper and mix it with sodium carbonate. I'm going to take copper nitrate and mix it with acetic acid. I'm going to see what all of those do. Okay, and if I'm using a spot plate, I can keep track. Let me show you what a spot plate is. I can keep track of what is going on. So this is something like a spot plate. Okay, so you have a small reaction. You can keep track of what's going on. Okay, and you're going to have 6 knowns and 6 unknowns, and then you're going to mix them and figure out which one is which. Does that make sense? Okay, so one of the questions says, how many mixtures are you going to have if you're mixing 2 together? So kind of think like this. So I have 6 things here. And I have 6 things here. I guess I don't have to mix. So I would have like about 36 things. Okay. I probably won't do this diagonal but I won't know. Yeah. Okay. So So you are going to have to write a procedure. You can do this in class on Thursday, or you can do this before and be ready to go, okay? That's not part of the pre-lab, but that will help you be prepared for the lab, okay? So you also have to make sure your pre-lab is done, okay? I want to get through all of the topics. Today is our last day to work on chapter 7 topics. I like to get through that, and then during work time, you can work on the pre-lab. The second part of this lab is also unknowns, but this is with solids. So the previous one is solutions. Part 2, you have 4 solids. We are going to have cornstarch, baking soda, baking powder, and sugar, and salt. And then there's 5 unknowns, and they're mixtures of these compounds, okay? And in this lab, you get the knowns. So you have 4 knowns. You'll have an unknown, and then you'll also have vinegar, water, and an iodine solution. And based on these, you'll be able to figure out what is in your unknown. So your unknown is either a mixture of 2 or a mixture of 3 of these compounds. Okay, so part of this is you're going to need to make a procedure. So before Thursday, I would write my procedure, or you can do it in class, so it'll just take longer in class. Okay, let's see. Before you start either of these parts, part 1 or part 2, you need to check with me, and I'm going to read your procedure and make sure it makes sense, okay? Or you can walk me through it. But that's part of the pre-lab, is that you have to check off with me before you start. You have to show me your procedure, and I have to initial it. So that's part of the pre-lab. Remember that I have to initial before you start your experiment. Okay. You can also ask me on part 2 with the solids if you have the right answer. Okay, and I can tell you if you are right or not. All right, so that is lab 5. Questions on lab 5. That's on Thursday. Okay, let's go through the rest of the chapter 7 topics, and then we will have some more time. Okay, this is our first topic. We're going to talk about hydrogen bonding. Okay, so if it's a covalent molecule, it can have intermolecular forces. One of the intermolecular forces, the forces between the molecules, is called hydrogen bonding. So this is the definition of hydrogen bonding. It's when a hydrogen atom bonded to O, N, or F is attracted to a lone pair on O, N, or F. So these are the two things that we have to look for if the molecule is going to have hydrogen bonding between molecules of the same type of compound. So we have to have hydrogen attached to N or F. If you say NOF, that's like a mnemonic device you can remember. So we have to have hydrogen attached to NOF. And then we also have to have a lone pair on the nitrogen, oxygen, or fluorine. Okay. So here is an example. We know that this is the Lewis structure of water. We know there's a hydrogen attached to an oxygen, so the first rule is satisfied. We also have a lone pair on the oxygen. That's the second rule that's satisfied. And so what's happening is the hydrogen is getting its electrons pulled by the oxygen. So this is kind of positively charged. And it's going to interact with the negative electrons, the lone pair on the oxygen. And that's this hydrogen bond interaction. It's not really a bond, it's like a positive and negative charge interaction. So if we want hydrogen bonding within molecules of the same compound, like water with water, then both of these have to be true. If we look at water, water supplies both. Water has a lone pair on an oxygen, water has a hydrogen on an oxygen. So if we want the compound to interact with water, it only needs one of these rules to be true, and then it will interact with water through hydrogen bonding. Okay, so that's important because there is an ALEKS topic called identifying hydrogen bonding interactions between molecules. So we need to know the structure. Sometimes they give us the structure, but if they don't, we need to think about what the structure looks like. So we have the name, and then we have the structure. So the first thing that we're going to do is we're going to check. So this column, we're looking for, does this molecule hydrogen bond with other molecules that are also N-chloromethylamine? Okay, so we're looking for, 1, is there a hydrogen on N, O, or F? Yes, that's true. So the rule number 1 is satisfied. The second thing we're looking for, is there a lone pair on N, O, or F? That's also true. If both of those rules are true, then yes, it will have hydrogen bonding within itself, or between molecules of itself. Okay? If this one is yes, then this question is, will this molecule hydrogen bond with water? If it has both of those two things, if it has a hydrogen on NOF and it has a lone pair on NOF, it can hydrogen bond with water. So that's yes. Okay, the next one is fluoromethane. This one they don't give us the structure, so it would be helpful to see the Lewis structure just to check for lone pairs. So this one we have a carbon in the center, and then we have 3 hydrogens. Doesn't matter where I draw them. Oh, and then we have a fluorine with the lone pairs. Okay, so this we're asking, does this have hydrogen on nitrogen, oxygen, or fluorine? No. This one doesn't. Okay, does that make sense? It has hydrogen, but the hydrogen is not bonded to NO or F. Okay, that's why we need to draw this one out. We need to know where the hydrogens are. Okay, so if one of those rules is not true, then it can't have hydrogen bonding within molecules of itself. Okay, so this one is no. Then let's go to the water. So we know that we don't have, so our 2 rules. We have hydrogen on the, and we have lone pair on the. Okay, this one, do we have a lone pair on nitrogen, oxygen, or fluorine? So this one we have a lone pair on the fluorine. So this rule is true, this rule is not true. As long as one of these is true, then it will hydrogen bond with water. So what's going to go on here is that this lone pair can interact with the hydrogen on the water. So because this hydrogen is on a really electronegative atom, nitrogen, oxygen, or fluorine, it's going to have a positive charge. And then this lone pair on the electronegative element is also, this is very negative. Oops, and so then this can interact with that. That is the definition of a hydrogen bond. So we're just like checking the definition. Checking to see if it works. Okay, question so far. Okay, the last one, acetic acid. So for acetic acid, let's erase this. They gave us the structure. Do we have a hydrogen on nitrogen, oxygen, or fluorine? It looks like we do right here. Hydrogen on oxygen. So that's true. Is there a lone pair on nitrogen, oxygen, or fluorine? There is. There's some here, one here, one here, one here, one here. So this is true. If this is yes, this column is also automatically yes. That's like a trick. Okay, let's do one more. More practice. Okay, this one is confusing. This comes up a few times. So this is HBRO. This is an acid. So the structure does not match the formula for this one. So when you see this, okay, when you see HBRO, HClO comes up, I think HIO might come up. Any of these acids, the structure has the H and the O together. So this is one that I would put on my note card because the structure doesn't match the formula. Okay, that's just confusing. I don't know why they're making it complicated. Because it doesn't follow, does it follow the, yeah, I guess it follows the, anyways. So this one, does it have a hydrogen on a nitrogen, oxygen, or fluorine? If we draw it correctly. Yes, this one has, this rule is correct. How about this one? Is there a lone pair on the nitrogen, oxygen, or fluorine? Yes. So there's a hydrogen on the, and there's a lone pair. There's actually two lone pairs. So this one would have hydrogen bonding between molecules of the compound. And then if this one's yes, it can also hydrogen bond with water. It has those available sites for hydrogen bonding. Okay, this one, bromomethane. So this one, let's see, so this one is kind of like the last one we have. Bromomethane. Okay, so this one, is there hydrogen on nitrogen, oxygen, or fluorine? There's hydrogens, but they're not on nitrogen, oxygen, or fluorine. So that's not true. Is there a lone pair on nitrogen, oxygen, or fluorine? There's also not one. Okay. So this one will not have hydrogen bonding between molecules. And because both of these are not true, then it can't hydrogen bond with water. Okay. All right, last one is ethane. Do we have hydrogen on nitrogen, oxygen, or fluorine? Nope. Do we have a lone pair on nitrogen, oxygen, or fluorine? Also, no, we don't have nitrogen, oxygen, or fluorine. If you don't have nitrogen, oxygen, or fluorine, then you can't have hydrogen bonding. You can't have hydrogen bonding with water. Okay. Do you feel okay about that one? We'll keep moving. Okay. All right, next topic. I have a list here. Identifying important intermolecular forces. So hydrogen bonding is a very important intermolecular force. Another one is London dispersion forces. So let's just quickly go over what these are. I need to stop. Okay. Okay, so London dispersion forces is where we have a molecule that the electrons are moving around the molecule, and just for a second, we have a dipole. So we have a negative side of our molecule and a positive side of the molecule, and that can induce a charge in another molecule where we have a negative. So this side is going to push the electron, or pull electrons towards the it's negative. And so then we have these, it's a really weak interaction between molecules. Okay. It's called London dispersion forces. This happens in all covalent molecules. So as long as it's covalent, it's going to have this dispersion force. Okay. If it's ionic, it does not have intermolecular forces because it's not a molecule. Okay. So I've seen that come up in ALEKS a few times. Not very often, but just watch out. If it has a metal in it, then it can't have intermolecular forces. Okay. But otherwise, if it's a molecule, then it will have this. The next one is if it's polar, it will have dipole-dipole interactions. Okay. So we have this. This is a formaldehyde molecule. We have this polar bond. So overall, this molecule has a negative side and a positive side. I know that because it's not symmetrical. We have an oxygen on one side that's going to pull electrons. And then these molecules are going to be like kind of like a magnet. We have a positive side and a negative side, and then this positive and negative side can interact with each other. And because this is a permanent dipole, a permanent charge mismatch, then this is a little bit stronger force. Okay, and then we already talked about hydrogen bonding. Okay, where we have these two rules that are satisfied. Okay, so that's the intermolecular forces between molecules. So now we can do one of these topics. Identifying the important intermolecular forces in pure substances, compounds. Okay. So this first one is silane. So it's helpful also to know the structure of these. So this is silicon. Silicon is right below carbon. Actually, if I draw this on my whiteboard. There we go. Okay, so the first one is silane. Silicon is right below carbon, so it has 4 valence electrons. And then hydrogen each brings 1, so we've got something like this. Okay. So is this a molecule? Is it covalent? This is covalent. Okay, it has only, it has no metals. So it's going to have dispersion forces. If it's a molecule, it's going to have dispersion forces. Is this polar? Is it unsymmetrical? Is there one side that would be positive and one side that's negative? No. So that can't have dipole-dipole. If it doesn't have dipole-dipole, then it probably doesn't have hydrogen bonding. Okay? That's generally the rule. Okay. We already saw formaldehyde. That was in our notes, but let's go ahead and draw that one out. So formaldehyde, we have carbon, we have an oxygen, and we have 2 hydrogens. So this one is a molecule. It doesn't have any metals, so it's going to have dispersion forces. Is this one polar? Is it unsymmetrical? Yes, it's polar. So this word should make you think of polar. Is it polar? Is it unsymmetrical? So our electrons are moving this way. We're going to have a positive side and a negative side. So this is going to have dipole-dipole interactions. And then for hydrogen bonding, we just have to check those rules. Is there a lone or a hydrogen on NOF? Is there a lone pair on NOF? Okay, well, there's a hydrogen over here, but it's not attached to the oxygen. So this one's not true. So there cannot be hydrogen bonding between formaldehyde molecules. Okay, next one is hydrogen chloride. They're not telling us the formula, so we have to know what that is. Does anyone know what hydrogen chloride is? Good. So HCl. I can make my L. Okay, let's draw our structure. Okay, this one is a molecule. There's no metals, so it's going to have dispersion forces. Is this one polar? Is it unsymmetrical? Yes, this one's polar, so it's going to have dipole-dipole. Is there a hydrogen attached to nitrogen, oxygen, or fluorine? So there's no nitrogen, oxygen, or fluorine, so it can't have hydrogen bonding. Okay, great. Last one is ammonia. Do you guys remember what ammonia is? That's one you have to know what it is. Good, NH3. Good. You should also memorize the structure for this one. Okay, so NH, these are H's, if you can't tell. Okay. Is this one going to have dispersion forces? Yes, it's a molecule, no metals. Is this one polar? Is it unsymmetrical? Yes. So this one, the electrons are going to move towards the nitrogen. So the hydrogen base is going to be positive, the nitrogen is going to be negative. Is there hydrogen bonding? Yes, good. There's a hydrogen attached to a nitrogen, and the nitrogen has a lone pair. So both of our rules are satisfied. This one's going to have hydrogen bonding. Okay. Do you think you can do one like this, or do you want to do another topic? Or do you want to do this one over? We're good? Okay. All right, you guys are flying through. Okay, let me go back to my list. The next one we should do is predicting the relative boiling point. This one is tricky because there's not really, this one's like a reasoning question. Okay, I think I have a slide on this one. Let me see if I can find the slide. Okay, So this is what you're going to look for if when you're doing this topic, okay? So if there's a metal, so like aluminum, or if you have an ionic compound like sodium chloride, anything that's a metal or an ionic compound is going to have a high boiling point. So imagine trying to boil salt or boil metal, okay? You're going to have to put a lot of energy. The boiling point's going to be really high. If there's any gases, those are gases like at room temperature. So like O2, F2, Cl2, carbon monoxide. Those are all really small molecules. It does not take very much energy for them to boil. So their boiling temperatures are like in the negative Celsius, okay? So if it's a gas, it's going to have a low boiling point. If you have a hydrogen bond, so if you're comparing, so the other thing I should say first is that the bigger the molecule, the harder it is to boil. So if you have a big molecule, it's going to be harder for it to boil. If you have similar sized molecules, then you can start looking at intermolecular forces. So if you have very similarly sized molecules, one has hydrogen bonding, that's going to make the molecules stick together more. They're going to have a higher boiling point, okay? Polar molecules will have a higher boiling point than non-polar molecules of the same size, okay? All right, so those are kind of our tips for this question. So let's go back here. Okay, so we have these 4. Okay, so let's think about silver. What is Ag is silver? What is silver? So think about yeah, it's going to be a high boiling point. So we're going to pick that one as the highest. We don't have any other metals. That's going to be highest. Okay, these 2 molecules are very similar. Do you notice they have the same carbon chain? The only difference is the oxygen is in different spots. Okay, so these are going to be really similarly sized. So if they're the same size, then we can look at the intermolecular forces, like hydrogen bonding, dipole-dipole. Also, we have argon. Does anyone know anything about argon? What is argon? Argon is a noble gas. Argon is a gas at room temperature. So this one is going to be the highest boiling point on our list because it's a noble gas. It's a gas. Okay, it's already gas. We didn't have to boil it at room temperature. Okay, then we have these 2. So what are you noticing about these 2 besides that they're similar? Do you see any intermolecular forces? So when I look at these, I see anytime you see an OH group, that's going to tell you it's going to have hydrogen bonding. So if it has hydrogen bonding, it's going to be harder for those molecules to boil because this has another spot for those molecules to stick together. So if it has hydrogen bonding, it's going to have a higher boiling point than if it doesn't. Oops, I picked highest here. I meant to put lowest here. Lowest. Okay, so this one's the hardest to boil. It's a metal. This one's going to be the next hardest because it's a molecule. It's a long, not really long. It's a 3 carbon chain molecule, and it has hydrogen bonding. This one's going to be the 3rd hardest to boil, and this one's going to be the easiest to boil, the lowest boiling point. Easiest. Okay, does that make sense? Okay, so this is just all about reasoning, figuring out what you have on your list, and just thinking through it. Okay, let's do this one. Okay, so when I go through these, I look for anything short and see if I can figure this out. So what do we know about calcium bromide, CaBr? We have a metal and a non-metal. So that's going to be an ionic compound. That's going to be hard to boil. So this one's going to be the highest. So try to get out of the way the ones that are pretty easy. Okay, then let's look at these ones. So let's see, we've got 3 carbons, and we have 3 carbons, and 3 carbons, 4 carbons. This one has 4 carbons. This one has a bromine. So look on the periodic table, or we could pull it up. How big is bromine? Bromine is 79. Bromine is very big. So everything else being equal, bromine is, if it's big, then it's going to have a higher boiling point. Okay, so I'm gonna think that this one's gonna be the next highest boiling point because of the bromine. Okay, let me see what else we have. So these ones the same except the OH. So oxygen is 16 plus 1 is 17. Nitrogen is 14. So these ones are probably pretty similar in mass. If they are within like 1 atomic mass unit, 1 or 2, then you can look at hydrogen bonding. Okay, this one has hydrogen bonding. This one doesn't. So I'm going to say this one is the easiest to boil. And because of the hydrogen bonding, this one's going to be the third one. So if I was doing this on a test, I would be more careful and I would calculate the molecular weight. Just add these all up. Because this one looks like it's pretty close. So if this is wrong, it's probably because this one doesn't weigh as much as this one. Okay, let's check. Okay, that's fine. So if they're really similar in size, then you can go off of intermolecular force. Otherwise, you're looking at mass and if it's ionic or covalent or a gas. Okay, how are you feeling on this one? Do you want to do another one? Or are you good? How are we doing? We're okay on this one? One more? Okay, yeah, let's do another one. Okay, same thing. So let's see. Looking through, I'm going to notice this one right here. We have F2. I know that that is a diatomic gas. Okay, so any of those dark green elements, those ones always come as a pair, and they're always gases. Okay, iodine and bromine are heavier, so they're sometimes liquids, but these are, this one's going to be a gas. Okay, so this one is, it's not highest, lowest. My bad. This one's going to be the easiest because it's a gas, fluorine gas. Okay, then let's go back through. These ones to me are looking kind of similar. Their connectivity is just different. We've got like an oxygen and an oxygen and an oxygen and nitrogen. This one doesn't have carbons. It just has nitrogen and oxygens. 1, 2. So this one, if I added these up, this one's going to weigh less. Okay, so if it weighs less, that's going to be easier to boil. Okay, now I'm going to look at these two. These ones are bigger molecules. There's more like carbon plus carbon plus carbon, carbon plus carbon plus nitrogen plus carbon. This one has 2 oxygens. So because these are really similar in size, we're going to look at hydrogen bonding. So do either of these have hydrogen bonding? Oops, this is like... So if I look at this one down here, I have a nitrogen attached to a hydrogen, and I have a nitrogen with a lone pair. This one's going to have hydrogen bonding. So this one is going to be the hardest to boil out of my list. This one's going to be the next hardest because of the size. This one's a little bit smaller, and then this one is a gas fluorine.
So that has hydrogen bonding, it's the hardest?
If they're similarly sized molecules, yes. So size matters more than intermolecular forces.
What if it's just a metal?
If it's just a metal, so think about trying to boil a metal.
Pretty hard.
Pretty hard,
So
yeah. So it'd be the hardest, yeah. Ionic and metals are hardest to boil. So look for those, look for gases first, then look at size, then look at intermolecular forces. Okay, better check it. Okay, so hopefully that's not too tricky. Let me know if you get stuck on that one. We have 2 more topics. We're going to look at specific heat capacity and then phase transition. Specific heat. Okay, so if you have taken physics, this is something that should be familiar to you. This chapter is kind of like the physical chemistry part of chemistry. It's kind of the overlap of chemistry and physics. So for this type of question, we need to use an equation. This is the equation we're going to use for this type of question. We need to use, so this is the Q equals M times C times delta T. Okay, so in this equation, have you guys seen this in physics? You didn't see it? Okay. Okay, this is kind of like overlap of physics and chemistry. So Q is heat. So you need to watch out. Is heat absorbed or released? So is it going in or out? So watch out for that. Okay, M, can anyone guess what M is? Mass, good. M is mass. C is a constant. This is called our specific heat. This is always the same for the specific type of compound. This is a constant. Okay, and what is T? What is usually T? Okay, time. It could be time. This one's going to be temperature. That's a good point. T can also be temperature or time. But here it's temperature. Okay, and it's delta T. So if it's delta T, we don't have to convert to Kelvin because it's a change. So that will help us with our Alex topic. So we always do temperature final minus temperature initial. So the final temperature minus the initial temperature is this delta T. And it can be in Celsius because our increment scale on the Celsius scale and the Kelvin scale are the same. They're the same increment. Okay, so this one is using this specific heat capacity. So that's our C to find a temperature change. All right, so this question is going to say something like you have a reaction and it's in a water bath. So what that is you just have a bath, like there's usually some kind of glass container and you put water in it, and then you put your reaction in the water bath. Have you ever seen that before? Maybe? Okay, so this just helps hold the temperature constant, or it helps you keep track of the temperature. Usually what happens is you want to modulate the temperature. If you want to change the temperature and you put a water bath on the outside, and then you can stir from the outside. Anyways, okay. So here's my reaction. It's in a water bath. That's what's going on. Okay, so it says the chemical reaction takes place inside a flask submerged in a water bath. The water bath contains this much water. So that's a mass. That's our mass. So I'm going to write down is what I know. I'm going to erase these. So my mass is 3.90 kilograms of water at 37.5. So this is my initial temperature. So be really careful on the temperature. So this one starts at 37.5 degrees Celsius. Okay, during the reaction, 71.3 kilojoules of heat flows out of the flask and into the bath. Okay, so think about what's happening. We have our flask. The heat is flowing into the bath. So what's going to happen to the temperature of the bath? It should go up. So at the end, we're going to expect this to go up. So watch out for that. Well, we want to check, make sure that goes up. Okay, so that is Q. That's the heat, the energy that comes out of the bath. So that is 71.3 kilojoules. Okay. And into the bath. Calculate the new temperature of the water bath. You can assume specific heat capacity of water is, okay, they're giving us C. C is 4.18 joules, and then this is our unit, joules per gram times Kelvin. But we can use degrees Celsius, that's fine, because we have the same increments. Okay, this one says round to 3 significant digits. It will not have this on the test, so I need to practice looking at my numbers. This has 3, this has 3, this has 3. This also has 3. Everything has 3, so my answer has to have 3 significant digits.
How is that one?
Joules per gram Kelvin. Per gram. Okay, but that's the same as, for this question, it's the same as degrees Celsius. So we're not going to convert for temperature. Okay, so I've written really big. Let me... I have another whiteboard. Let's do that. Okay, then I still have my numbers over here. Okay, so let me plug in what I have. So I have Q, so Q equals MC delta T. T, remember this is temperature final minus temperature initial. Okay, we're looking for the final temperature. So we have Q. Q is 71.3 kilojoules. M is 3.90 kilograms. C, I'm going to run out of space again. 4.18 joules per gram Celsius. And delta T, we have temperature final minus temperature initial was 37.5. Parentheses. Okay, so this is just an algebra problem now. We're looking for the temperature final. Okay, so the first thing that I'm going to do is I'm going to divide this number by these two numbers. So 71.3 kilojoules divided by 3.9 kilograms times 4.18 joules per gram Celsius equals temperature final minus temperature initial, which was 37.5. Okay, so let's stop here. Look at our units. This one is kilojoules. This one is kilograms. So technically, we should convert both of these. This one should be in grams. This one should be in kilojoules. This one should be in grams. So to do that, I'm going to multiply this one by 1,000. And I'm going to multiply this one by 1,000. So if I convert, can you see how the thousands will cancel out? So I don't really need to convert for this problem. So if that's going to confuse you, convert. Okay, if that's confusing, if that makes sense to you, don't convert. Okay, does that make sense? Okay, because the thousands are going to cancel out. So I'm going to not convert, and it will work out. Okay. Oh, the other thing that we need to keep track of is the heat flows out of the flask into the bath. So this is a positive number. I forgot to check. Sometimes this will be a negative number. But because it's flowing into the bath, we are keeping track of the mass of the bath, the initial temperature of the bath, and the final temperature of the bath. So this is going into the bath. This should be a positive number. This is not always a positive number, so watch out for that. When it would be negative is if the temperature of, it says the bath loses this much energy, or this much heat flows out of the bath, then that's going to be negative. Okay, let me pull up our Alex calculator. So this is the last one with lots of math. The last question is just looking at a graph. So let's see. Okay, so I've got my 71.3. And then divide that by 3.9 times 4.18. Okay. All right. And then now I have this number 4.373696. I'm going to leave that in my calculator. I'm just continuing to solve for the final temperature. Okay, and this should go up by 4. Okay. Okay, so this is the final temperature of the bath. I'm going to round this up 41.9. Okay. All right, let's look for one that has the water bath flows out. Okay, this one, I don't know why, but this one I miss a lot. So let's see if we can get this one right this time. Okay, so we're going to use this equation. Q equals mc times delta T. The water bath contains 8.4 kilograms of water. So that's my mass. So let's just plug in what we know. That's our mass. Whoa. It's still water, so C is going to be the same. I think every time on this problem, C is always the same. Because it's the specific heat of water. 4.18 is C. M is 8.4. And it starts at, so the temperature final, minus the initial temperature. Initial temperature is 34.1. Okay, and then 141 flows out. So this is where it will be negative. This one is leaving. Okay, let's see if we can, I don't know why. If I get it wrong, we'll read the explanation. These ones I often get wrong when it's flowing out. I'm not sure. Okay, so we're going to solve for the final temperature of the water bath. So I'm dividing by that on both sides. So negative 141 divided by 8.4 times 4. Okay, let's see. All right, so my temperature should go down by 4 degrees, 4.01. So my initial temperature was 34.1, and it should go down by 4. Okay, and then everything in this problem has 3, so I'm going to put 3, 30.1. Okay.
Wait, so it went up, down by 4?
Heat flows out of the bath and into the flask.
Why 4?
Because I just, this is how much energy left. This is the mass of the bath times the specific heat.
Mm-hmm. So,
I just did the algebra to find 4.
oh, okay. Oh.
Okay, any other thoughts on that? Okay, let's check. Okay, that worked that time. Okay, questions on that? Does that make sense? Do you want to do another one of these, or do you want to move to the last one? One more? Okay, let's do another. Okay, this is another flows out. So watch. Yes. Watch for which direction the heat is flowing. Okay. All right. So same thing. What do we have? And then I think we're also always solving for the final temperature. So it says during the reaction, 113 kilojoules of heat flows out of the bath. So I'm going to say that's negative. It's leaving the bath. Okay. Into the flask. Okay. And we have the mass. The water bath contains 4.40 kilograms. So that's my mass, 4.40. The specific heat of water is always the same. That's a constant depending on your substance. This question always seems to ask about water. And then delta T is our final temperature minus our initial temperature, which is 39.1. Oh, I'm running out of space there. Yeah, that's our initial temperature. Okay, so just read through the problem, make sure that it's always giving you the same stuff, especially on the test. Sometimes there will be one that is slightly different. I can't remember if that happens on this question or not. Okay, then I'm just solving. I'm dividing by this number in the front. So then I have, this will equal the final temperature. Okay, so let's take my calculator. Right, 113 kilojoules flows out of the bath, divided by the mass of the, oh yes, it is negative, thank you. Divided by the mass of the water times the specific heat of the water, 4. And then this is going to tell me the temperature change. So the temperature is going to go down by 6. Okay, and our initial temperature was 39.1. So then our final temperature should be 32.95. We need 3 sig figs, so we're going to round this 9 up. So it's going to be 33.0. Okay. I'll check that. Okay. All right. You see you can do that one? Okay, we've got one more. One more type of question. This is identifying phase transitions on a heating curve. Okay, so for this you need to know, this is a heating curve. Let's draw a heating curve. Let me draw one. So I've got my curve. Along the bottom is heat added. Along this edge on the y-axis is temperature. Okay, and then I have some important pieces of the graph. So I have this initial temperature increase, and then it stops increasing. Then I have another temperature increase. It should be the same slope. My bad. Let's try and make it more slope. Same slope. So slope, slope, same slope. And then the temperature stops changing. We also have a final temperature increase. Okay, so every substance has a heating curve that looks like this. This down here is when it is a solid. Okay, so this curve, this part here. Then we have this period between this point, and this is when it's a mixture between solid and liquid. And if you are stirring your container with solid and liquid substance, and it's like perfectly insulated, it's not going to change temperature. If you get it perfectly at equilibrium, it's not going to change temperature until all of the solid has turned to a liquid. Okay, this is also in physics. So if you took physics, you should also talk about this. Okay, so then from this point to this point, everything is at a liquid, but now it can increase in temperature. Okay, so from here to here, liquid. Okay, so what do you think is happening here at this? This is like a temperature stall. We're staying at the same temperature. Yeah, we start changing to a gas. So it's going to be a liquid, and some of it's also a gas. And this is our phase transition between liquid and gas. Okay, so as the substance goes from a liquid to a gas, it sits at the same temperature. Then once everything is changed to a gas, then it can increase in temperature, and everything along this heating curve is a gas. Okay, all right, so you need to know that. This is something that I would put on my note card so that I'm ready for the test. Okay. All right, so it says, a pure solid sample of substance X is put into an evacuated flask. The flask is heated at a steady rate and the temperature recorded as time passes. Here is a graph of the results. Use this graph to answer the following questions. What is the melting point of X? So based on what we just talked about, what is the temperature that this melts?
Like 9 or 8?
So this is the heat added. Yeah, so at like 9, it's all melted. That's how much energy you add. But it's asking about the temperature. So look on this side.
Oh, yeah.
Okay, yeah, so about 105. So put that in, 105. I don't know, sometimes this is picky about decimal places. We'll put a decimal and see what happens. Okay, next question. What phase of X would you expect to find in the flask after 33 kilojoules per mole of heat has been added? So this is just reading a graph. So we're adding 33. So over here, 30, this is 35, this is 33. So we're going to go up. So what phase do you expect here? This is going to be a mixture. If it's a flat line, it's a mixture. Liquid and gas. Yep. Once it's hit here, then it's all gas and starts going up again, the temperature. So this is going to be liquid and gas, and we can pick more than one. Okay, let's try another one. A pure solid sample of substance X is put in an evacuated flask and heated. Here is our heating curve. What is the boiling point? So this is where you need to know. This first one is where it melts, goes from a solid to a liquid. This is the boiling point, goes from a liquid to a gas. So what is the boiling point for this substance? Let's see. So this is 140, 160, this is 150. Like 155? So be careful in your graph reading. I think the most errors I've seen on this type of question is people just don't read the graph carefully. Okay. And then if we add 16 kilojoules per mole, what is the phase? So 10, 11, 12, 13, 14. Oh, that's not 20. 10, 2, 12, 14, 16. So this one would be, this is on this part of the curve, we have a liquid and we have a gas. Okay. All right. Do you want to do another one of these? Or does that make sense? One more? Okay. Let's see. One practice. Okay, so same thing. We have a heating curve. What is the boiling point? So remember, this is the melting point. This is the boiling point. That says 40. Does that say 40? No. Yes. This is 80. Okay, 80, 90. So 85 is our boiling point. I'm going to put a decimal. I don't know if it needs a decimal. What phase would X you expect to find after 5 kilojoules? So that's right here. So this one is on the flat part, so that's going to be solid and liquid, solid and liquid. If it's on the positive part of the graph, then it's going to, so this part would be solid, this part would only be liquid, this part would only be gas. If it's on this phase change area, then it's going to have 2 phases. Okay. All right, we don't have a lot of time left, but we are through all the topics. So we've got like just under, like, I don't know, 15-ish minutes left. So make sure you have your pre-lab for next time. Remember your procedure for lab 5 if you want to do that before. And then make sure you're working on your Alex topics. Alex is due on the 15th.